Hello everyone, and we'll take a look at how meshes can be used in a variety of different applications and how you can generate toolpaths for these mesh models, and also how you can repair and fix meshes if you're working from point cloud data or scans. And we'll go through a few examples and applications where you might typically find mesh geometries for your CNC process in here. So we're going to give you a quick run through of different types of applications where you might find meshes that you might get mesh geometries from, and then we'll also go through how we can use these mesh geometries to program and produce toolpaths in here. So typically mesh geometries, you'll be basically finding mesh geometries in applications like, for example, foot scans and a variety of different applications in here. So you could be using a handheld scanner to scan, orthotics or foot scans to recreate, and also you can use mesh models for restoration. Now the meshes could be exported from those scanning devices or systems in forms of STL, which is known as stereolithography, or OBJ, or anything that's in mesh representation, or triangles. So those could be mesh geometries, and both Rhino and Visual CAM can read a variety of different types of mesh file formats, starting with OBJ, STL. These are the common types, and there's also several other mesh file types, and any file format that you can import into Rhino or Visual CAD, you can generate and program toolpaths with those mesh models. So what I have here is basically a scan representation of a foot model here. You can see this is a mesh geometry, so as you select it, it says a mesh added to selection, and made up of triangles, or basically these are facet data. You can see those mesh wires being displayed in here. So the process of restoration work is generally generated using mesh models. So this is just one of the examples of a mesh geometry in here. Now meshes could also be generated for a variety of different applications, like in cases of architectural woodworking, where you can actually bring in mesh models. In this case I have a cabriole leg in here, which has some details, very fine details on the mesh model, as you can see here. So these could be also, it could be scanned from a restoration part, or you could be, using a piece of a cabriole leg and adding some details and, like artwork to it, like as Jim pointed out earlier in his presentation. So where you can take an existing model and then, be creative to add your own designs and artwork to it. And then, so if you're using ZBrush or other CAD systems to model these, you would be exporting them either as OBJ or STL. So those are mesh geometries, and you can import those geometries into Visual CAD or Rhino and then program your toolpaths with it. Now, I also have a few other examples where you could be using mesh geometries in dental applications. Mesh geometries are also widely used. So you have these scans of your dental implants, and so different applications you might be getting a scan, and then these could be easily effectively machined using Rhino CAM and Visual CAD CAM. So in this case you have a bridge here, and you can basically be programming this from multiple different orientations on a rotary axis, 4-axis, or even if you have a 5-axis machine tool, you could use a combination of indexed and simultaneous 5-axis applications. Now mesh geometries could also be created for mold work, where you could be creating these mesh geometries for like a restoration, or if you're doing a restoration of an antique part, or you probably would want to basically bring those in and be able to machine them. So a variety of different applications where you can use mesh geometries and mesh models in here. So typically mesh geometries can be used on a wide range of different applications, and these file formats are either like STLs or OBJs, and you can bring those mesh models in here. So here's another example of a core box, like a cavity of a mold, which was exported as an STL or a mesh geometry, and you can use these models to efficiently generate toolpaths and send this posted G code out to your CNC machine tool to have these machined.
With that, I just wanted to interject a little bit. A comment about mold making. Actually, we do have customers using meshes in mold making. You would think that, mold makers typically use solid models and derive all of the molds from, airtight and watertight solid models. For the most part, that's true, but we have quite a few customers who are using meshes, exclusively meshes for mold making, things like, medical implants and things of that sort. One of the reasons for that is we have really nice shelling tools, splitting and creating of male and female portions, cavities and cores for the molds, as Uday is going to show later on. So it is an interesting application for actual mold making, precision mold making as well. So, and then we have some customers who are using it for industrial parts. You would think that, meshes don't lend themselves well to industrial parts, but, one application that we find very interesting is this restoration of old vehicles, or even aircraft. Now, we have a company in New Zealand who's using it for bringing in, scan data of parts, obsolete parts that they don't have any drawings for, all of these World War II aircraft, and they actually bring it in as scan data, clean it up, and these are actually industrial parts or widgets, if you will, and they use our system for machining. So thanks, Uday.
Thank you, Joe. So, as you noticed, meshes could be used in a variety of different applications. Now, we'll take a look at an example of how we could use mesh geometries to program some 2-axis or 2.5-axis toolpaths. So, to go ahead and demonstrate that, I'm going to go ahead and locate one of these sample models in here, and I'll bring it into Rhinoceros, and I'm also going to do the same thing in our standalone Visual CAD/CAM as well. So as you try to open or import a mesh geometry in Rhino, you'll see this STL import options. Now, typically, mesh geometries are unitless, which means they do not carry any specific units, whether they could be in inches, millimeters, centimeters, or whatever units they may have been modeled and exported in from the CAD system. So since if you're not the designer, or if you receive the file from your customer, you wouldn't be sure what units they were modeled in. So when you import those files, you'd be seeing this import options, and I'm just going to go pick the default units as inches and then load the part. So as you load the part in here, in this particular case, I have a part that's prismatic, meaning there aren't any sculpted surfaces or sculpted bottoms. It's basically a part that has straight extrusions. Now, parts like these you can program using 2-axis or 2.5-axis machining operations like pocketing, profiling, facing, drilling operations. Now, once you bring in a part, the first thing I would go back and check is the model unit. So I'm going to go into the mill module. So the model units here, it shows as inches since we imported the file in inches, but the dimensions or the extents of the part that we're looking at, is that in the correct unit. So we want to make sure that this model can actually represent the correct unit. So if I go into a stock definition in here, for example, in the mill module, you'll see that the model extends, the length, width, and the height are showing up as 127 inches. So, by looking at these extents, it tells me that 127 appears to be really large for a part that is in inch units. So what I would need to do is either switch. It appears to be that the part has to be in millimeters. It may have been exported in millimeters, but when we imported it, it happens to be in inches. So we need to basically scale the model down to inches, or we can switch the units to millimeters. So there's a couple of ways you can do it in Rhino. Is if you right-click on the units, you can go to unit settings, and you can toggle the units from inches to millimeters, and you can also scale it to millimeters. So in this particular process, I would like it to be 127 millimeters instead of 127 inches. So I don't want it to scale it by an additional factor of 25.4. So I'm going to select no to it. So basically now the model is in millimeter units. And now if you check the stock dimensions, they are still 127 millimeters in length and width, and the height here is 12.7. So I would need to reorient the part and machine it. Now, if you want to switch the model units back to inches for machining it, you can right-click on it, go to unit settings, and switch it back to inches in here. And you can select yes for scaling. So this will basically convert the and scale the model down to inches. Now if you go back and check the stock extents in here, you'll see that now it's 5 inches by 5 inches and half an inch thick. So the model appears to be in the correct dimensions for which you want to process or program your toolpaths. So once you have the model units established correctly, you could orient your part for machining. So I can choose the orientation by using the orient part command in the CAMJam's machining browser. Under the setup, you have the orient geometry, and you can orient it right here. And then you can define your stock material in here. Go to stock, box stock, it computes the stock, and then you're pretty familiar with the process of how you can establish your origin in here by going to set world coordinate system. You can choose to establish the origin to the stock box, ISZ, southwest corner. Now, when you're working with mesh, we currently have the model oriented in here, and also we've established the correct dimensions in units. So it's an inch units. The model is 5 by 5 by half an inch thick, as you notice the extents of the model in here. So now we are ready to machine program toolpaths. Now for programming a 2-axis or 2.5-axis toolpath, we actually need curve geometries, or we would need face edges. Now in the case of STL or mesh geometries, there aren't any face edges as you would find in a surface-based model. So to be able to create some of these face edges from the model, you could take advantage of some of the curve tools that are offered to you in Rhino, and also the predefined machining region tools that you can find under the machining objects browser in RhinoCam. Now one of the curve tools that I'm familiar with in Rhino is in the curve modeling tab. You have create a mesh outline command. So you can use the mesh outline command, and basically mesh outline command works with solid surface and also mesh geometry. So in this case, since we are working with the mesh, I'm just going to highlight the mesh and then press enter. And you'll notice that it automatically creates those curved geometries for the holes and also for the inside pocket and also the exterior boundary around the part. So now you can use these mesh the region curves as regions to program your toolpaths. Now these could be pocketing or facing or whatever operation that is appropriate for the model that you're working with. Now with the curve extraction tool, the mesh outline, you'll notice that it was unable to produce some of these curve boundaries for the interior pocket, the step pocket in here. So you can take advantage of the tools. Under the regions tab, you have what's called a flat area regions, and you can just go pick this face in here, and it'll automatically create those machining regions as well. These are predefined regions. Now these predefined region tools are available to you in RhinoCam. You can also find these in Visual CAD/CAM and also in our other CAM plugins as well. So in Rhino, you can use the curve extraction tools. One of the tools is the mesh outline. There's other tools like section curves and other tools. You can use them as well. In addition to that, you can also use the predefined machining region tools that you can find under the regions tab. Now once you have these created in here, you could program your toolpath. So you could do a pocket operation. You can use the predefined regions that you just created in here. You can select the region, and then you pick a tool for it, and then program your toolpath. So that creates your pocket operation. Now let's take a look at how the same model can be processed in our standalone product, which is Visual CAD/CAM. So I'm going to go ahead and import the same model into our flagship standalone system, Visual CAD/CAM, and we'll go ahead and take a look at how we do the orientation and how we would be able to bring in the file. So now when you import this part into Visual CAD/CAM, you will notice that it'll prompt you if the model units that you have is currently in inches, you'll be actually prompted whether you wanted to switch the model units to millimeters. So in this particular case, I actually had the units for Visual CAD/CAM already in millimeters, but now I switched to inches. When I go back and reopen this part, you will notice that it prompts you with the units change, and it also tells you that the part seems to be or appears to be too large to be an inch part or an English part units, and it'll ask you, would you like to change the units, model units to metric? So based on the extents of the part, Visual CAD is smart enough to determine that this part may be too large for an inch unit. So you can choose to set it to millimeters. You can select yes, and you'll notice that the model is automatically imported in millimeter units, and you can check the extents in here. It gives you the same length, width, and the height, which is 127, 12.7, and 127. So once you have the model, and the units and dimensions established, if you want to switch the units back to inches, you just click the units button down at the bottom. And in this particular case, we would need to switch the units from millimeters to inches. In addition to that, we would also want to scale it, so we pick yes for scaling. And now you'll notice that the model units is switched. So if you go over to Analyze and click on Part Information, it gives you the length, width, and the height, or the extents of the part based on the current orientation. And the workflow remains the same. You can go ahead and orient the part like we did it in RhinoCam. So the same controls are available in Visual CAD/CAM as well. You can establish your stock geometry, and then you establish your origin. So the workflow in the CAM on how we orient the part, how we create the stock and establish the origin remains the same. Now the curve extraction tools in Visual CAD can be found under the Curve Modeling tab. You could go into the Curve Modeling tab and use a wide range of tools in here. You have flat area regions, where you can pick a flat area, pick a face, and this will automatically create those curve boundaries in here. As you can see, the interior and the exterior boundaries are created. You could also use the same tools again to create the boundaries around the step pocket, or you could use the predefined machining regions tool to create and pick the face. It'll automatically create the two boundaries in here, and then you can program your toolpaths. So there are several different tools available for extracting curves under the Curve Modeling tab in Visual CAD, as well as tools under the Regions tab using these flat area regions. You can also create surface boundaries, silhouette. So you can refer to the help section in Visual CAD to learn more about these curve extraction tools. Now the next thing we're going to take a look at is how we could use our mesh module to be able to import some point cloud data and create meshes from those point cloud data and effectively be able to machine them. To demonstrate this, I'm going to go into RhinoCam, and I will go ahead and import a model in here, which is basically a point cloud, and we're going to work with the point cloud data in here. And if you do have any questions, folks, as we go along with this presentation here, please feel free to post those questions in the questions panel, and we'll do our best to answer them for you. So what I currently have here is a point data that's imported into Rhino. You can see it's a scan data made up of a whole bunch of points in here. And I'm going to go into the RhinoCam menu, and in version 2018, both in RhinoCam and Visual CAD/CAM, we have a new module called Mesh. So as you select Mesh from the menu, you will notice that this brings a browser interface very similar to what you've seen in our mill and other modules. So this is the browser has 5 different tabs. We have Create, Modeling, Inspection and Modification, Repair, and if you're going to use an application for another application like a 3D printing, you can also generate supports, and you can export or generate G-codes for 3D printing application. Today's webinar, we are focusing more on machining of meshes for a subtractive manufacturing process, which is like a CNC milling process. So we'll be focusing more on the mesh tools. So once we have a point cloud data, point cloud geometry that's imported, you'll see that the point cloud information appears in the data tree in the mesh browser. So we would like to, in order to machine this, we would need to create an actual mesh geometry from this point data. So we have a very nice tool called Create Mesh from Point Cloud. So as I select this, I'm prompted to select the point cloud data. So I'm just going to highlight the mesh, the point data in here to create a mesh from it. And once I right-click, you'll see that all the mesh creation options are in here. So I'm going to use these default parameters and then select Create. So in this process, it's going to use the parameters that you specified in, and it'll create a mesh from the point data that you have. So now the point data could be generated through scans, other different applications. You could be provided with the point data from your customer or from your user, and you can generate a mesh from the point data. So you'll now notice that the mesh has been created from the point data. I'm going to hide the point data in here so you can easily view the mesh geometry. So I'm going to go into a shaded mode so it makes it easier for you to view the mesh. So we were able to generate a very nice mesh from this point data in here. And you can see the mesh has about close to a million triangles. Now if you view the mesh here, you can notice that there are several holes on this mesh model. So you can go into the Repair tab and perform a diagnostic check to identify the holes. And if you perform a check for open edges, you'll see there's over 38,000 holes on this particular model. Now, to fix each of these holes manually, it's going to be a much large time-consuming process. It's going to probably take several man-hours to fix these holes in here. So one of the powerful tools that you can find in the mesh module is a command called autofix. So when you select the autofix command and run it, it'll automatically analyze the mesh geometry. It looks for holes, looks for self-intersections, and it automatically closes these holes to create a closed mesh. So this will result in a closed watertight mesh geometry. The autofix is a very powerful tool which automatically identifies the holes, the self-intersections, any incorrectly oriented triangles and normals, and automatically fixes those meshes. And this saves you significant amount of time when you have to fix meshes rather than having to do these manually, and it'll probably save you, hours of time. The autofix is a very nice tool and powerful tool that's offered to you under the repair tab in the mesh module. And as you can see, we are working with a mesh geometry that's close to 1,000,000 triangles, and the process of the autofix is very powerful in here, as you can see right there. So if I go back and perform a diagnostic check on this model again in here, you will notice that there aren't any open edges detected, so there aren't any issues found identified on this model. So we've now fixed the mesh. In the next step, we can take a look at how we could reduce the mesh or decimate the mesh for further processing in here. So if you go to the the Inspect and Modify tab, you'll see decimation or mesh reduction in here. You can use the Reduce Mesh command. You can select the mesh, and you can specify either by a triangle percentage or by a deviation in here. So I'm going to reduce it down by 70% and pick Reduce Mesh. So it's going to drop it from something that's closer to 1,000,000 triangles, and we should be seeing down something closer to a 30,000 mesh count in here once the reduction is completed. Now, performing the mesh reduction does not, distort the geometry, or it preserves all the features. As Jim pointed out earlier in his presentation, you'll notice that the model is being still preserved, but the number of triangles is reduced, so it makes it easier for your downstream processing, which could be toolpath generation, or it could be other applications in here as well. Folks, again, if you do have any questions, please post those questions in the questions panel, and we'll do our best to answer them for you as we go along in this webinar. So on this particular mesh model in here, I'm going to turn on the display of the mesh wire so you can actually view the triangles on the model in here. And you can see that the triangles are not very uniform. So to make the meshes more uniform for machining or any other downstream applications, we have some very nice tools under the Inspect and Modify tab. One of the tools is called Remesh. So we can do a remeshing, and you can specify the remeshing criteria in here, where you can set an edge length and the number of iterations. And I'm going to put in an edge length of 50,000 and run the remesh command. So this basically results in creating uniform triangles. So it makes the mesh more uniform, so it makes it nice and easier for machining or any other downstream applications. So in this particular webinar, we are focusing on machining. So as you can see here, it creates much nicer uniform triangles upon remeshing this model. Now we can also perform operations like mesh smoothing. We can select the mesh geometry in here and specify the vertex shift direct from smoothing and specify the number of iterations. I'm just going to leave it as 2 iterations and perform a smoothing on the model. So this basically smoothens out or evens out any bumps and variations on the model in here. You can also apply the mesh smoothing to specific areas in here. So you can use precise controls where you can specify a radius. There's you can pick certain areas on the mesh. In this particular case, I'm going to use an area to smoothen out, so I can actually graphically select these areas in here. So you can basically refine certain areas and specify your parameters for mesh smoothing, or you can even do mesh reduction or mesh remeshing in certain areas. So you can basically specifically select certain areas of the mesh to apply certain processing to it. So you can see that there's a powerful set of tools that's available to you in the mesh module that would allow you to effectively edit and modify the meshes.
Uday, I knew this question was going to come up when we were practicing the webinar. One customer is asking what's the difference between the rhino reduction and our reduction. So when you get a chance, maybe you can do a side-by-side comparison of rhino reduction. I don't know if you're set up to do that, but if you can, that'll be great.
Sure, I can certainly go with that here. So I'll probably take an example of maybe one of the models where we can do a comparison side by side. So Rhino also offers you mesh reduction, but the mesh reduction tools that is offered in the Rhino CAM's mesh module is much more powerful and robust, and it gives you a much better result on the mesh reduction in here. So basically what I have here is a model of a corbel, and I'm going to make a copy of this in here. So I'll just basically make two copies side by side, so that way we can apply the reduction using using the Rhino CAM's mesh module, and then we'll apply the same using the Rhino's mesh reduction tool. So over here, the one on the left, I'm going to apply the mesh reduction using the Rhino tools in here. So I'm going to go into mesh and apply the reduce mesh in here, and I'll just reduce it down by 50%. So I'm processing the mesh reduction. You can see how long it's taking in Rhino to process it in here. And I'm going to take this model in here and apply the same mesh reduction in Rhino CAM. I'll reduce it down by 50%. So you'll see that the Rhino is the one on the left is more distorted in here, as you can see over here, and and compared to the one in Rhino CAM is much more much more cleaner. So as you compare them side by side, so you can actually evaluate you can see the two differences between the two models in here. The one on the right is more cleaner, it shows more of the details, but you're losing much of the details as you perform some of the mesh reduction tools with Rhino. So I hope this helps. Now moving on, the next thing I'm going to go over here is how we could perform some of the mesh offsetting tools, and also we'll take a look at how we can perform mesh booleans as well. Now in order to go with this, I'm going to go ahead and bring in this example, which is basically a mold. And one of the things I'm going to do here is you can see that there are several different meshes. So these are made up of multiple different mesh geometries in here. So if I perform a diagnostic check on this model in here, you will notice that there are several open edges in here. So in order to perform any Boolean operations or being able to offset, I need to have a closed mesh. So first thing I'm going to do is a feature called stitch and close. It's a very powerful feature that's also included in the mesh module. So I'm going to select the model and automatically run a stitch and close command. So this basically stitches all the open meshes into a closed watertight mesh.
Yeah, if you notice, there was 420 meshes in this model. So
yep, it's now down to one mesh in here. I have one other mesh that's probably on a different layer that's hidden. We'll talk about that in just a moment. So we have the mesh now. Basically, it's a closed watertight mesh, and I'm going to perform a offset. So you can find it under the modeling tab. You can select the offset command. You can specify your offset distance and tolerance. So specifying a positive offset distance will basically offset it towards the outside. If you specify a negative offset distance, it's basically going to shrink it, meaning it's going to offset towards the inside. So right now we have two meshes in here. As you can see, there's the original mesh and the offset mesh. So I'm going to hide the one of the meshes in here. Okay, so I'm going to use the offset mesh, and I'm going to perform a Boolean. So I'm going to do a subtract to create a cavity from the mold model. So I actually have a mesh box modeled already in here. It was on a layer, so I just made the layer visible. I'm going to perform a Boolean subtract command, and I'm going to pick this as my base mesh, and then I'm going to pick this as the mesh to subtract from. And you'll notice that the Boolean process is so robust and fast, and you can see how quickly you're able to perform the mesh Boolean. So these are very powerful mesh editing tools that are offered to you in the mesh modules. Now once you have this mesh ready, if you want to go ahead and reduce the mesh, I could go into inspect and modify, do a mesh reduction on this model, reduce it. So I now reduce the mesh, and you can see that all of the information in the mesh is preserved, so we are not losing much of the information from the model. I'm now going to go ahead and switch over to the mill module so we can generate some toolpaths from it. So
One quick comment here. What Uday had actually did here was he took a core part, offset it out, and then he subtracted it out of a block of material. So in effect, what he got was a cavity with a little bit of an offset. So you could potentially use something like this for mold making for shells. If you're doing some plastic shells, now we have an offset on the cavity, and that'll give you the space where the plastic will flow through. So this is a very powerful tool that can be used for mold making. Thanks, Uday.
thank you. So I now have the model prepared and ready for machining. So the workflow is very similar. You go ahead and switch to the mill module. You can orient your part for machining. And once you have it oriented, you can define your stock geometry and then start programming your toolpaths. I could go from a roughing toolpath, so I'm going to use a 3-axis roughing. I can specify an end mill, click generate. Now since I reduced the mesh, you'll notice that the computation of the toolpath is much faster. Had I not reduced it, it may have taken longer than what it did currently. So decimating or reducing the mesh not only speeds up your toolpath computation, also makes it, you may not require such a high precision of the mesh, high in a number of triangles on the mesh to program your toolpaths for these models. And as Jim pointed out, so basically when you program and generate your toolpaths, what you see is what you get. So when you run a simulation and verify it, that's the result, what you would end up seeing when you machine the actual part on your CNC. So we went through a process of roughing. Now we can take advantage of some machining regions in here. I can just pick this face and extract some boundaries. You can see there's 2 boundaries created. Now I can pick this boundary and program a toolpath. I could start with a parallel finishing, or I could do a finishing in levels like a horizontal or Z-level finishing and generate the toolpaths from the model. So you can use the curve extraction tools under the predefined regions tab, or use the native tools that are available in Rhino and Visual CAD to create these machining regions and use those machining regions for containing your toolpath to specific areas in the model. So in this particular case, I created the region, but I never selected the region in the operation. So I can just go back in here and choose the machining region and then accept it and then pick generate. So the toolpath will now stay contained to the predefined region I just selected in here. So I created the predefined region under the machining objects browser in the regions tab, and after defining the region, I selected the predefined region and the control geometry in the operation to contain a toolpath. So this is how we can efficiently program 3-axis toolpaths on mesh geometries in Rhino CAM. So you can apply all the different 3D toolpaths depending on what is required for this model for programming your toolpaths. Now we could also program 4 and 5-axis toolpaths. I'm going to give you a quick run through of that as well. Again, if you have any questions, folks, please feel free to post those questions in the questions panel, and we'll do our best to answer them for you. So what I have...
There's a question from one of our customers. How many millions of dollars does the mesh module for RhinoCam cost? Let me take that question. It's not millions of dollars. It's actually $1,000. So it's the mesh module itself is add-on, or you can buy it separately, so you don't even need RhinoCam. So if you're only working with mesh, you can just buy that module, and it's an add-on for $1,000. Hope that answers the question. All right, well,
Thank you, Joe. So again, I have a model in here, which is a architectural woodworking, a post that you would like to program on a rotary axis or a 4-axis if you have a CNC equipped with a rotary table. Now, if you wanted to, process this model in here, you can refine the mesh. So if you take a look at the mesh wires or the triangles on the mesh, you can see some of these mesh triangles are not very uniform. And to make it more uniform, you could actually go into your mesh module and run a remesh command in here. You can specify an edge length. So I'm just going to go ahead and put in an edge length of 100 thousandths, and I'm going to do a remesh. And you'll see that even on such a large model with such a small edge length, you'll notice that it processes the remeshing operation into such an efficient and a quick manner in here. You can see that it's processing the remeshing operation, and it probably takes anywhere from a few seconds to maybe a minute or so, depending on the complexity of the geometry. But you can see the speed at which it's being performed and the quality of the result that you're seeing here. It's much more uniform triangles that you generate on the mesh in here. You can also apply mesh smoothing and remeshing to specific areas, target areas. If you wanted to certain areas to be refined, you can apply those as we talked about in one of the earlier examples in here. So once I have the model prepared in here, I can switch back from the mesh module back into the mill module, and we can program our toolpath. So I'm going to go into 4-axis. I'm going to choose a parallel finishing operation. So since I want to do a finishing operation on it, we'll grab a tool for this, specify the cutting conditions in here. You can choose to establish a low and the high values, that is the extent of the length of travel for the finishing operation, and then pick generate. And the toolpath is being generated on the mesh model here. So we are basically programming a 4-axis toolpath. So we looked at how we could do a 2-axis, 3-axis. Now we are looking at some multi-axis toolpaths in here. We are generating a 4-axis parallel finishing toolpath, and we did process the mesh. We did apply some remeshing to create uniform triangles, and you can see that within a reasonable amount of time, your toolpaths are generated.
A comment about those uniform triangles that Uday is talking about. One of the reasons that we would recommend using the refinement to get you triangles with very constant side lengths, the reason we recommend that is this will result in much better surface finish when you finish the part. So even though the detail, the same amount of detail, if you have long skinny triangles like in the original model, when you actually machine it, you're going to end up with a bad surface finish. So that's why this refinement, where we are reducing those triangles to triangles that have very similar aspect ratio. By that I mean the lengths of the sides of these triangles are about similar. You will get a much better finish. Thank you.
Thank you, Joe. So I'm running a quick simulation here, cut material verification, so you can see the result of the simulation of the toolpath that was programmed. And basically what you see in the simulation is what you would end up seeing on the machine part itself. So this is one of the examples where you can use mesh models on programming 4-axis. There could be other applications where you could also be using programming 4-axis toolpaths in here. So while we are waiting on this simulation to finish here, as you can see, it just got done. As you can see how nice and clean the simulation looks. And this is what exactly you would expect on the machine part, which would require, less amount of hand finishing or refinishing, and it'll be ready for your other applications. Now finally, I'm going to cover how we can use mesh models for 5-axis applications. And
so we're running very close to running out of time, so I just want to take a minute here and pause and ask our customers who are watching the webinar, do we have any questions for Jim? While we have Jim, this might be a good time if you have any questions. Okay, we'll wait for questions. One of our customers says, thank you, Jim. So yeah, thanks, Jim, for hanging in there. But we still have one final piece that Uday is going to show, which is the 5-axis part. So if you just hang in there for a few minutes, we'll show that too. So thank you.
Thank you, Joe. So what I have here is a scan model of a face. As you can see, this is a mesh model, an STL. So to be able to program toolpaths in 5-axis, you could program indexed or positional 5-axis operation, also known as 3+2, with STL or mesh models. Now, to be able to program a simultaneous 5-axis toolpath, you would actually need a surface-based model or a surface or a NURBS model to be able to do a 5-axis simultaneous toolpath. However, since we are working with a mesh in here, what we could do here is use the mesh model as a geometry to check for gouge, or basically as a gouge check geometry. So the tool, the toolpath would be projected onto this model, but then you're still going to be using an underlying surface model to have the tool remain normal to it. So you can use tools that are available to you in Rhino, where you can create a surface from the mesh, where you can extract some curves, or you can do a slicing using the mesh module in Rhino CAM, and then use those curves to loft a surface. So what I've done here is created some curves and built a surface from the actual STL model in here. So this is the surface I've created, and the surface is basically placed beneath the actual mesh model in here. So the 5-axis methods are available, the simultaneous available in our premium configuration. So I have a 5-axis surface normal machining operation programmed in here, and I've selected the surface model I created in here, the one that's on the interior here, as my drive surface. So the tool would remain normal to the drive surface that's going to be machined. And under the gouge check tab, I have selected the actual mesh geometry in here, the STL model, as the geometry to check for gouge again. So when the tool path is generated, it's generated based off the normals of the underlying surface, but then it's being projected to the actual mesh model. So as you run a verification here, the tool path actually is on the mesh model, but the normals are derived based off the actual surface model that we selected as the drive surface. So this is one of the ways how you can efficiently program 5-axis toolpaths, simultaneous 5-axis toolpaths on mesh models. And if you have any additional questions, we can certainly help you answer these questions on 5-axis programming. You're welcome to contact us or reach out to us. You can post questions as well. So there's a toolpath animation where you can see the 5-axis toolpath is following the mesh geometry, but the tool stays normal to the drive surface which we created and selected for 5-axis programming.